In this example, we're going to look at a family of convergent series. So we're being asked to find positive integers k so that the series from 1 to infinity of n factorial squared over kn factorial converges. So notice that both the numerator and the denominator here have factorials in them, so that's a nice big clue that we probably want to use the ratio test. Another thing to notice here is that these series terms are all going to be positive. So when I do the ratio test, I don't need to worry about the absolute value bars because everything's already positive anyway. All right, so if we look at the numerator and the denominator here for our ratio test, here is our a sub n, here is our a sub n plus 1. So now let's do some simplifying things here. Let's put the n plus 1 factorial with the n plus 1 factorial squared with the n factorial squared. That's this first term here. And then put the kn factorial with the k times n plus 1 factorial. That's the second term here. All right, so notice that when we do some simplifying, n plus 1 factorial squared is n plus 1 factorial times itself. Each of those we can pull off an n plus 1 and be left with an n factorial. So we have n plus 1 times n factorial squared, or each individual piece squared. So the reason why I've written it this way is so that we see that cancellation easily. The second thing to notice is that we've got k times n plus 1 factorial here. That's kn plus k factorial. So if we start simplifying that, we start at kn plus k, then we subtract 1, we subtract 2, and keep going until we subtract k minus 1, which leaves a plus 1 here, and then we get a kn factorial left over. So then these kn factorials will cancel. So after simplifying, we get the limit as n goes to infinity of n plus 1 squared over the product of these factors here. And notice that there are k of them, right? We've got 1 here, 2, there'd be a plus 2 here, a plus 3 here, all the way up to plus k. So there's k factors here. All right, so let's just start analyzing what happens for different integers k. Well, first, let's start if k equals 1. Well, if k equals 1, the only thing we get is n plus 1, right? Because if k equals 1, then this would be n plus 1 here. We wouldn't have any of these other ones here. So if k is equal to 1, we get n plus 1 squared over n plus 1. That simplifies to n plus 1, and certainly that goes off to infinity. So that means that if k is equal to 1, the series diverges. What happens if we plug in 2? Well, if we plug in 2, we get 2n plus 1. The next one would be 2n plus 2, and that's where we stop, right? Because we stop when this plus whatever is the same as the coefficient on the n. So we would have 2n plus 2 times 2n plus 1 on bottom. So this behaves like n squared over 4n squared, which if that reduces to a fourth when we take the limit. Okay, so what happens then afterwards? Well, if n is greater than 2, then we've got a degree of this polynomial. When we multiply it out, we get k. Notice that that's the same thing is true for 1 and 2, right? If k is 1, the degree of the denominator is 1. When k is 2, the degree of the denominator is 2. In general, then, when the degree of the denominator here is k, because we're going to multiply all of these n's together k times. That was what I mentioned before, that the number of factors in the denominator is k. So if k is greater than 2, the denominator's degree will be greater than the numerator's degree. So if the degree of the denominator is greater than the degree of the numerator, we're guaranteed that the limit will be 0. So if k is 2 or bigger, we get a limit that is less than 1, either 1/4 in the case where k is equal to 2, or 0 when the case where k is greater than 2. And either way, those are both less than 1, so For when k is greater than or equal to 2, this series converges by the ratio test.